Sometimes you find yourself between a rock and a hard place. Like when the parts in your inventory cost a very, very high amount of money and at the same time have a very long lead time. This is the case in, for example, airline inventory optimization. Today we're going to talk about the question whether you should focus on better demand and lead time forecasting models or whether your efforts are better spent on better optimization. Welcome to Inside Opt.
Many companies are struggling with that conundrum. Do I need better forecasts, or do I need to find a way to derive better decisions from the forecasts that I'm having? Let's look at the example of an aircraft repair shop today. The client comes to you and says, look, we have a fantastic operation here. We get the assets back in the air very, very quickly. In fact, we could do worse there, but the inventory costs are eating our lunch. Just on the expensive parts, we're spending $14.5 million per year just in inventory costs for those parts. And this makes our business not very profitable. Is there a way to do better? So what is the issue for this aircraft repair shop? Well, the assets that are being repaired are very, very expensive. They might cost between $10,000 and $50,000 per day that they're out of commission. At the same time, the parts that go into the plane are not inexpensive either. They might cost somewhere between $50 and $200 per day just to put them into inventory. And you can procure these expensive parts very quickly. They have lead times between 30 and 40 days. Now, of course, your client uses some form of forecasting. So, for example, to predict for the assets that are coming in for scheduled maintenance, to predict what kind of parts they might need, they employ what is known as a digital twin. And those digital twins, they give you a reasonable idea of what kind of parts might be needed, for example, when repairing an aircraft turbine. However, they're not perfect, and you cannot make them 100% perfect because of aleatory uncertainty. There is a combinatorial aspect to this problem, of course, and that is that when you're doing a repair, depending on what the cause is why the asset is coming to maintenance, you might need a bag of parts in order to get the repairs done and to bring the assets back into production. And if you don't have all parts in that bag, then you would not be able to actually complete the repair. What is the issue now? What is the task before us? Well, we are planning for 3 weeks. And these 3 weeks will take place from day 40 to day 60. And during this time, we are expecting assets to come in for scheduled maintenance. We have digital twins that tell us a rough idea of what kind of parts these assets might need. And now between day 0 and day 30, we can order those parts. Remember that they have a lead time between 30 and 40 days. So we can order those parts and then hopefully we'll have all the parts that are needed in order to get all the repairs done, while at the same time keeping our inventory costs under control. If you give this problem to your very motivated student who just comes out of an OR program, they might say, okay, great. The digital twins give me an estimate of how many parts I'm going to need on what day during this 3-week schedule. So the digital twin might come back and might say, well, I need 0.9 axial compressors, 0.8 high pressure turbines, half an exhaust, 2.4 fan blades, and 0.6 inlet ducts on that day. Then the second step would be that you're somehow trying to model what you want to optimize for. Is it to get your assets back in the air? So the time value that the assets that are unnecessarily grounded for a longer period of time than they would have to be to get the repair done because you're delayed because you don't have the parts, is that your target? Is it the cost of the inventory? Is it the total number of days that your assets are delayed? So regardless of the respective value of the asset that is being delayed, all of those might be possible. And the issue is that this motivated young individual that tries to help this company will ask the stakeholders to make trade-offs that they do not know what they are. So you might have to choose one, constrain others, but you do not really know what a constraint, say, of cost of inventory has to be low or equal 600,000. What does that mean for the value of assets that are unnecessarily grounded, right? The time value that they're being delayed. And before you actually know that, it's very, very hard for a stakeholder to do that. Similarly, if you wanted to somehow take a weighted sum of these objectives, well, what is the respective value that you should give, right? The respective weight that you should give each of these is not really something that you can do before you've actually seen the data. So it's not very prescriptive, let's put it that way, if you're doing this. But this is the common way on how such a problem would be modeled. And then in the third step, you would then take the expected demands from your digital twins, optimize this, and then come back and say, wow, this is fantastic. I can lower your inventory for those 3 weeks to $270,000. Currently for the company, it's around $900,000. So you're like, hey, this is the power of optimization. This is OR. Let's put a post on LinkedIn because OR has a marketing problem. Look at what the fantastic potential is of using optimization. And in the expected demands, the readiness loss here would be 0 and the delays would also be 0. Problem is, if you start simulating the solution that comes out of this deterministic optimization, it looks very different. The real loss, the time value loss of the assets that are unnecessarily delayed is actually 2.3 million. And that is not acceptable for an aircraft repair shop. That you're bringing in your assets this late. Also, total number of delay days is close to 74. Absolutely not doable. The inventory costs in reality are also slightly higher, but they would still be massively less than what the shop is currently using. But this is obviously leading to a completely unacceptable service level for the repairs that would be done. What do you learn from there? If you want to optimize your bed, it's a bad idea to start with a maximum likelihood sleeping position or an average sleeping position. You need to take the variability and the number of different futures that could occur into account when you're doing the optimization. The moment you forget that, you're going to end up with abysmal solutions that look fantastic on paper, but are abysmal in practice. And of course, the folks at the company know this. They are practitioners. And these practitioners probably have found a way to somehow keep their inventory reasonably at bay, but while taking into account that there is uncertainty in these forecasts and that they need to train for this. What is a common way to do this? Well, a common way to do this is to add external parameters. For example, you could add safety stock levels. You can add time buffers, right, to account for the uncertainty in the lead times. Or a suggestion that I got from Michael Watson, thankfully, is to put a bound on the stockout probabilities for each part and every day. And using this, you can improve your solutions. The problem is, as you're doing this and you're setting these external parameters, you actually still don't know, well, if I set the stockout probability to 5% or if I set it to 2%, what does that actually mean for my inventory costs? So again, it's not very prescriptive to ask the stakeholder to do this outside of the model. Moreover, you really do not know what it actually means for your KPI. So it's not a calculated risk unless you calculated it, as Navid Abdali said in his famous book. So if you add these external parameters and you want to actually try and assess what does this mean to my KPIs, you would need to run a simulation again. And the simulation would then come back and say, well, your readiness loss is about $13,000, your inventory costs about $908,000 for those 3 weeks, and your delay days are a little bit shy of 4 days. So something like 7% of your assets are delayed a day, and their time value cost is $13,000. This is kind of your starting position in this hypothetical case that I'm presenting you here, right? So for 3 weeks, this would cost $908,000. How can we improve this? Well, using a completely different kind of solver where you don't ask the user to give you trade-offs before you actually do the optimization, you would start with probabilistic forecast. So don't use your digital twins to give you an aggregate number of parts that you're going to need on a particular day, but break it down into the individual turbines and the corresponding causes. So for example, for the first turbine, there might be 2 different reasons as to why it's being brought in. Either it's going to need an axial compressor and a high pressure turbine, or it might need an exhaust. For turbine 2, there's a 60% chance that we're going to need 4 fan blades. Mind you, if you only have 3, you can't do the repair. You need 4. 4 fan blades, 1 inlet duct. There's a 30% chance that you might need an exhaust, and there's a 1% chance that you need an axial compressor. And these are mutually exclusive. So obviously you can have many of those different kind of parts bags, if you want to call them that. But this is the idea, put a probability mass in front of each of those parts bags, and then make sure you have all of them in order to progress the asset and get the repair done. Mind you, if you're using these probabilistic forecasts, so if you're working in inventory, you dread the following situations. What do you do if you have obsolete parts? If you have erratic demand patterns, rarely needed parts, or ramp ups and ramp downs, right? As assets go out of commission or come in for the first time for maintenance, you're dreading these situations because this is not kind of a stable state, and you need to forecast these things, and it's very, very hard to come up with just one number, when in reality you would like to be able to say, look, I really do not know whether it's this bag part or that bag part, and there's much more uncertainty in my forecast right now than there normally would be. Using probabilistic forecasts, this is exactly what you allow the machine learning to do. It can express that it isn't really sure, that there's much more uncertainty in terms of what might actually be needed. There is 2 other sources of uncertainty in our problem. We've just talked about the uncertainty in the demands and their combinatorial nature. We have uncertainty in the lead time. We're going to use an exponential distribution in order to handle that with a 10% standard deviation. And our initial inventory, which we're always planning to be 0, but there is a chance that there might be some leftover parts from the operation that happened beforehand. And of course, we're gonna take a maximum of 0 and the random variable, and the random variable is going to be normally distributed with a standard deviation of 1. What do we do in the second step? Now we identify everything that matters independently of one another, and simply have the user tell us what would be a fair value for the respective objective function and what would be an excellent value for the respective objective function. And then in a multi-objective fashion, optimize all of them at the same time, asking the solver to find the right trade-offs between these different 3 concerns that we're having here. Again, in the spirit of Michael Watson, to model the conflict and to find out what is the right trade-off between the different concerns that you're actually after. And then in the third step, now of course we're going to call seeker in this multi-objective setting. And here is the result that you would be getting in this case for a, this is a stochastic run. So this is one example of what you might be getting. You see here the different distributions that you're getting for your delay days, for the total time value cost of the grounded assets, as well as the inventory costs. And what you see here is that the model internally assessed is very, very close to what you would be getting if you do an external simulation. So the readiness loss here was internally assessed to be a little bit more than 97,000. In reality, it's about 100,000. Inventory cost was assessed at 431. In reality, it's 433. And the delay days was 28.5. And in reality, it's 28.8. Very, very close. And actually a really, really good solution for our client who said, look, I can afford that some assets will come out later. There are other reasons why things get delayed anyway, right? The labor needs to be scheduled. Something else is just in the way. So just the fact that all the parts are there doesn't necessarily mean this is going to progress anyway. So consequently, we can afford this, but paying $433,000 instead of $908,000, that is the difference between a profitable business and one that's limping by. Now, how do we get there? Well, let's look at the impact of scenario numbers. We have already seen that just looking at one future is a really, really bad idea. If you do that, you're going to end up with these, $270,000 in inventory costs and an assumed hallucinated no delays in assets and whatnot. In reality, though, it was an abysmal solution. So here we take our three different objective functions and turn them into a quality score. And I'm giving you a point kind of for every way of sampling 10 scenarios over here. This is what these gray points mean. I sample 10 different scenarios, and then I see, well, these 10 different scenarios, what do they think how good the solution is that I'm getting if I'm optimizing over them versus what it really is. So you have the hallucinated value here on the x-axis and the real value on the y-axis. And you see that with 10 different scenarios, you get quite a bit of variance between these scenarios, the solutions that you're getting over there. And it's kind of far away from where you want to be, which is this main diagonal over here, where the hallucinated value is the real value or very, very close to it. This here is the optimization credibility gap. If you ask me, this is the reason why so many companies are not using OR. It's not a marketing problem. It's not a lack of awareness. It is plain and simple because they know I am not properly prepared for the uncertainty that is there. And if I'm using predict then optimize, I'm going to be screwed. If I'm adding these external parameters, I might have to tinker with this myself, but at least I'm going to end up with a robust solution, even though I do not know how, whether it's necessarily optimal. And I know that I'm leaving money on the table, but far less than if I went with an optimization solution. So let's ramp up the number of scenarios. What if I'm having 20 scenarios? You see that this starts moving up. So the solutions that you're getting, the real value of the solutions is getting higher. And at the same time, the variance inside declines a little bit. Now we do another 10 experiments, sampling 10 times 50 scenarios. And you see that we are now getting really closer to what reality is. And we stop this experiment at 100 different scenarios where you see that there's not much variance between them anymore. And at the same time, you're really, really close to this main diagonal where the self-assessed value of a solution is close to the real value of the solution that you want. Now I can give you here the average over those 10 and compare that, and you can do that with Seeker also. You can compare that with a solution where you would optimize these external parameters, such as the value for the stockout probability that you can set. Now this still, because you're setting the stockout probability for a part, this still doesn't actually recognize the combinatorics in the problem, that you have these bag parts that you need to handle. And at different times, it might be more important to have a part in inventory than at other times. And this isn't reflected there. This is why you see a discrepancy here between them. But this is another way, and now you can use Seeker in order to do stochastic optimization, where again, you would use 100 scenarios to assess how good actually that probability is. But you have many fewer variables to assign in the local search than you would if you're actually setting the ordering schedule directly, rather than setting the stockout probabilities and then inferring from there what you need to order when. And now we come to the reason why you're watching this video. We want to investigate what the impact of imperfect forecasts is and how much of that can be mitigated by advanced optimization technology. So what do we do here? So far we have assumed that our digital twins give us probabilistic forecasts. They give us a distribution of what the true value of, for example, the lead time or the parts bag probabilities might be. Now, obviously, our digital twins will also not be perfect when estimating that distribution. It already alleviates a lot of the problems you have with point forecasts, in that the digital twin is now able to convey when it is more uncertain than at other cases, and to kind of give the optimization an idea of the shape of the distribution. However, it might not be able to estimate the true distribution perfectly either. So what are we doing now? Let's look at the parts bag probabilities first. What we do is we have an estimated probability for each part bag. So for example, 13.25%. And that estimate might be wrong. So we're altering it. We're turning it, in this case here, to 15.12%. And the way how we're going to alter the true probability for a particular parts bag is by 5%, 10%, or 20% standard deviation, depending on the experiment that we're going to run. And you see here this can be pretty significant in difference. This is a random example that I took from the data. Here you see that the parts bag number 5 here, the true probability that we're going to need this parts bag is 37%. And after the distortion, it's 41%. So there's a significant difference. As machine learners, we probably wouldn't be too happy if we would be observing this kind of deviation. Now, when it comes to the inventory level distributions, I told you before that it's a normal distribution with standard deviation 1. We're going to underestimate that variability by using standard deviation 0.5, or overestimate that variability by using a standard deviation of 1.5. And for the lead time distributions, again, in our true distribution, it's an exponential distribution with standard deviation 10%. We are again going to underestimate that by 50%. So instead of 10% standard deviation, we're going to look at 5%, or overestimate this by 50%, leading to a standard deviation of 15%. Now, if we do this, we have 12 different cases here, right? So we have 3 options here on how we alter the true parts probabilities that we have here by throwing 5%, 10%, or 20% noise on this. And then 2 options for inventory and lead time each, giving us 12 different experiments that we can run. Now, for each of those 12, we can do the tuned external parameter optimization and tune the level of stockout probability that we want in order to get a good result with respect to what our business is after. So this will be evaluated based off of 100 scenarios again, to see what is the optimal stockout probability that we should be using. And it turns out it's around 35% availability that we should be going for. And you saw that in the last slide, right? So we take this as our baseline, as something that is already very good. It is a tuned version. It doesn't have all the combinatorics. It doesn't actually compute the it doesn't actually compute the ordering schedule directly, but it does so indirectly by optimizing the stockout probability. Now, if we take the mean or the median, they're almost identical, so I'm only showing you one over here. The mean or the median value that we're getting if the original data that we're receiving is actually distorted in one of those 12 ways. On average here, we're losing 4.3% in performance. So instead of getting something around an overall quality of 777, we are down to something like 745 or something like that. Right, 744, around there. It's about 4.3% in hit that we're taking by our digital twins not being able to provide perfectly accurate probabilistic forecasts. And the other thing that I'm giving you here is also the minimum performance that we're getting over those 12 cases, the maximum performance that we're getting over those 12 cases, as well as the first and third quantile performances, so that you have an idea on how much this actually distributes. So it is clear we're taking a hit by not having even distributionally correct forecasts from our digital twins. Now what we're going to do is we're going to go back and actually optimize the ordering schedule directly rather than taking the detour of optimizing some stockout probability first. And this is the result that you're now going to get. So again, since we're sampling 100 different scenarios, what we need to do is we need to do this a couple of times in order to have an idea how good this really is. So for each of those 12 cases, we sample 10 times 100 scenarios, then do the order schedule optimization for it, and then look at the result. And what you're seeing here is that on average, so all these purple points are these 120 experiments that were run. By the way, I should add, these were 10-minute runs on a 170 core machine with 760 gigabytes RAM. So each of these points is a 10-minute run, which, you know, if you buy this on the cloud, costs something like $1.20 or so to do this optimization. Very, very doable, very, very affordable to do this and get these results. And what you see here is that on average, you're getting somewhere 762 or something like this. And this is only 2.1% worse than had you optimized your external parameter for the true distributions that you're actually going to see later. This is a very, very good baseline, and you're only 2% under it. And this for very, very significant errors that your digital twins are making over here, right? So, I mean, 20% standard deviation from the true values over here, the true part back values, is very, very significant. Similarly, underestimating or overestimating the true variability of the lead time by 50% is very significant. So I told you before that our lead time, the expected lead time varies somewhere between 30 and 40. So say it's 40, and the standard deviation of 10% of that would be 4 days that something might be delayed or come early. Now a standard deviation might be assumed to be only 2 days or might be assumed to be 6 days. And you know that it's very, very easy to be 2 standard deviations out. So suddenly we're talking about the very realistic chance that some parts will show up 12 days later than you expected them to be. This is very, very significant noise that you're having in here. And nevertheless, what you're seeing is this kind of quality over here. You're only 2.1% below a very, very reasonable baseline that you would do if you don't have a solver like Seeker available to you. Obviously, the best thing you can do is to have the true probabilistic forecast, get as close as you can to the true distributions, and then use Seeker on top of that. That overall is the best solution you can get, but barring the ability to provide those distributions perfectly, you can be assured that using a good stochastic optimization underneath will recover a lot of the losses that your digital twins are leaving. So in summary, what you're having here is that 50% suboptimality caused by the imperfect forecast is actually compensated by advanced optimization. And with that, I wish you always safe landings.